Hi, I'm Sam Martin from Texas Instruments DLP, here to talk about one of the many challenges facing next-generation augmented reality head-up display systems, sunlight. You may be wondering why somebody from Texas Instruments, a semiconductor manufacturer, is here talking about automotive head-up display, so we'll start with a little background. DLP supplies MEMS micro-mirror imaging devices to the automotive industry for head-up display applications. Our DLP 3000Q1 and DLP 5530Q1 chipsets are released and in production. They offer hermetically sealed packaging and extended operating temperatures required for automotive applications. Today, you can find head-up displays using DLP technology in the Lincoln Continental, and there are plans for 2 other models this year and 10 models by 2020. DLP has over 20 years of production experience in a broad range of applications, including digital cinema, 3D printing, and automotive head-up display. Current HUD architectures are based on either TFT or DLP technology. They're similar, except that TFT architectures emit the image directly, while DLP architectures use a diffuser screen to relay the projected image. This difference becomes important when sunlight enters the HUD optical system. Diffuser screens are passive optical elements that simply scatter the sunlight away, but direct emission displays like TFT contain sensitive electronics that must absorb all this energy. This becomes much more of a concern for future augmented reality HUD systems. So what makes augmented reality HUDs different? Conventional HUDs that can be found in cars on the road today are used to display secondary or duplicate information. They typically have a virtual image distance of around 2 to 3 meters and a horizontal field of view less than 10 degrees. To enable true augmented reality, the future of automotive HUD will demand wider field of view and longer virtual image distance to properly overlay digital content onto real-world objects. We're seeing a lot of activity around AR HUD in Europe and China. Many projects are targeting the 2020-2021 timeframe and have requirements for field of view greater than 10 by 5 degrees and VID greater than 7 meters. However, these increased virtual image distance and field of view requirements cause higher levels of sunlight collection and concentration, more than has been seen in conventional HUDs on the road today. In an effort to study this effect, I've been doing some simulations using a prototype AR HUD system that our team designed and built. This image shows the optical design consisting of 2 curved mirrors and a diffuser screen. You can see how the incoming sunlight rays are concentrated onto the screen plane. Increasing the field of view will demand larger HUD mirrors and therefore increase the sunlight collection area, meaning more sunlight energy will be concentrated on the screen. What's less obvious is that increasing the virtual image distance will cause the sunlight to be concentrated into a smaller spot on the screen. To understand this, let's take a quick dip into geometrical optics. Here we can see a simple thin lens system that results in a virtual image, similar to the way a HUD works. The source object, an emissive display panel or diffuser screen, is located within the focal length of the HUD optical system, causing the driver to see a virtual image projected and magnified in front of the car at some virtual image distance. The relationship between object distance, image distance, and system focal length is given by the Gaussian imaging equation. 1 over image distance is equal to 1 over object distance plus 1 over focal length. Keep in mind sign conventions, causing object distance to be negative in this case. Rewriting the equation, we can see that in order to achieve a longer virtual image distance, or greater z prime, we must make the denominator go to 0, or make z approach negative f. This is equivalent to moving the source object closer to the focal plane of the HUD optics. When sunlight enters the optical system, it tends to focus to the focal plane. The display source in conventional HUDs with shorter virtual image distance will experience relatively low levels of sunlight concentration because it is not very close to the focal plane. To achieve the longer virtual image distance required for augmented reality HUD, the screen must move closer to the focal plane, causing potential for much higher levels of solar concentration. And our simulations agreed. These images show the irradiance distribution on the screen inside TI's AR HUD prototype for 2 different virtual image distance configurations, 7 meters and 15 meters. Between these 2 configurations, we saw around a 2x increase in peak solar irradiance on the screen. These simulations were done with the sunlight source aligned with the chief ray of the HUD optical system, but we quickly discovered that off-axis input can be far worse. These two simulations show solar irradiance distribution on screen for on-axis sunlight on the left and off-axis on the right. Even though there's less total optical flux, the local irradiance can be much greater, causing potential for local damage to whatever the light is hitting. So, the longer virtual image distance and off-axis sunlight input clearly causes higher irradiance. But these are just relative changes. We need absolute numbers if we're going to make informed design decisions. What is the actual solar irradiance one might expect in these systems? To answer this question, we need an accurate sunlight model to predict solar irradiance and prevent thermal failure in the end product. An accurate sunlight source model needs to incorporate the sun's geometry, spectrum, and irradiance at Earth's surface. The sun subtends approximately a 1/2 degree disk in the sky, and after spectral filtering through the atmosphere can be up to around 1 kilowatt per square meter, with this spectral distribution. However, there's some inherent spectral filtering in the HUD system due to the windshield, glare trap, and other HUD optical elements that will attenuate this light. The simulations in this presentation assume around 25% of the sunlight actually makes it to the screen surface due to spectral filtering. The details of this are available in the white paper linked at the end. The next question was what input angle resulted in the highest level of solar irradiance on the screen. Using MATLAB Zemax scripting, I was able to scan the sunlight source across a range of angles above the HUD system. The plot on the right shows peak irradiance on the screen as a function of sunlight input angle. From this, we found that the worst case peak irradiance on the screen at 15 meter virtual image distance was around 57 kilowatts per square meter. It's important to remember that every HUD design is different, so this number isn't necessarily true for every HUD system. A comprehensive simulation must be done that incorporates the HUD optical design and spectral transmission properties of each component to accurately simulate solar irradiance. However, the general trend of increased solar loading in AR HUD systems remains. Whatever display technology is powering the HUD, whether a TFT panel or diffuser screen for DLP architectures, it must be able to withstand these higher levels of solar irradiance. So, to summarize, next generation augmented reality HUD requires larger field of view and longer virtual image distance, which leads to higher levels of sunlight collection and concentration. This solar loading must be simulated to predict and avoid thermal failure, and HUD architectures based on DLP technology use a diffuser screen that can tolerate these higher levels of solar irradiance. To learn more about solar loading in head-up display or general DLP automotive applications, feel free to follow any of these hyperlinks, or just visit ti.com/DLP. Thanks for listening.